So thanks for the introduction. Good morning, everyone. Today I will be talking about tracking drone orientation using multiple GPS receivers. And this is a joint work with my collaborators at IBM, Justin and Justin, colleague Ashutosh, and my advisor, Professor Romit Roy Chowdhury from University of Illinois. So needless to emphasize, fantastic applications are emerging in the world of drones. However, despite this excitement, why don't we see drones flying around us? Several instances of crashes and failure have happened. Clearly, drones are not any toys. They are deadly and they can kill people. So why do you think drones crash? When a drone is flying in space, it's constantly bending and tilting, and its orientation is changing continuously. And this precise information about how exactly it's oriented is necessary for stabilization. And inertial sensors like accelerometers, gyroscopes, and compasses are used for capturing the orientation information. However, things are not perfect. These inertial sensors can fail. And when that happens, drone crashes can happen. So wouldn't it be nicer to have an alternative for inertial sensors failure so that we can activate them as a fail-safe mechanism when the primary mode of sensing fails? So you already know that drones use GPS for localization. Can we leverage GPS for orientation sensing as well? So in this paper, we answer this question in the affirmative through our system called SafetyNet, which is a fail-safe mechanism for inertial sensor failures. So we use multiple GPS receivers for computing drone orientation. So at a high level, we place multiple GPS receivers on different wings of the drone. And as the drone is flying in space, it's continuously changing its orientation. And along with the orientation, the relative positions of these GPS receivers will change. And we are going to track these relative positions and convert that into 3D orientation. So in order to achieve an orientation accuracy of less than 2 degrees, we need a localization accuracy of less than 2 centimeters. So how can we reach there? This is a very strong requirement. So let's look at basic GPS. It gives you 3-meter accuracy. Clearly, this is not going to work because the drone is only 30 centimeters wide. However, note that we don't care about the absolute positions of the GPS receivers. We only care about these relative positions. Therefore, we can leverage techniques from differential GPS, which gives you relative position with a much better accuracy of 15 centimeters. However, still this is not sufficient because the drone is only about 30 centimeters wide. So in the rest of the talk, through several spatio-temporal information fusion of GPS carrier phases, I'm going to explain how we can achieve that goal. So here is the 3 key contributions. It is in the design of several differentials and filtering techniques around GPS carrier phases, which helps us in reaching our target goal. However, in order to explain that, I would first like to give you a background of differential GPS, specifically carrier phases and spatial differentials. So what is a GPS carrier phase? Your smartphones compute your location using propagation delay. However, advanced differential GPS techniques looks at the phase of the GPS signal. So in simplistic terms, I have expressed the range between the satellite and the receiver in terms of the GPS carrier wavelength. So this range can be divided into 2 parts. There is going to be an integer part, which is the integer number of wavelength, and then there is a fractional part. And your phase measurement is essentially capturing this fractional part of the range. Now, if someone would magically tell me what this integer part is, hereafter referred as integer ambiguity, then we will have a precise estimation of range with an accuracy of less than 1 centimeter. So seems like we are done, but we are not, because estimating the integer ambiguity is one of the hardest problems in the differential GPS, and we are going to spend more time on this later. So this is still a simplistic model of carrier phase that I have given you in terms of this integer part and the fractional part. In reality, it is going to be much complex because of other error terms like unsynchronized clock errors and atmospheric delays. So all of this contribute to a lot of errors in the carrier phases. However, again, keep in mind, we are not interested in absolute locations. We are only interested in relative locations. Therefore, many of these errors can be eliminated by simple differencing. So let me give you an example of what I mean. So you have a satellite and 2 GPS receivers. And I have expressed the carrier phase equation of the first receiver, including its error components. And similarly, I have expressed the carrier phase equation of the second receiver. Observe these two equations closely. Many of these error terms are correlated. Therefore, if we simply difference these equations, they are gone. So let me do further simplifications. So essentially, we achieved two things. First, by differencing, we eliminated many correlated errors. And second, observe the right-hand side. It has a factor R12 in the first term, which is precisely this relative vector between the two GPS receivers. So this is giving us a convenient model of measuring the relative positions directly, which is precisely what we care about. And the last equation has this uncompensated clock error. Without going much into detail, I would like to inform that by performing another similar differentials across different satellites, these clock errors can be eliminated as well. So even if you missed many of the details in this slide, the takeaway message is that three things. Carrier phases are noisy. By performing differentials, you can eliminate many correlated errors. And the second thing is that you obtain a convenient model of measuring the relative positions, R12, directly between the GPS receiver pair. And finally, by performing double differentials, you are eliminating almost all of the clock synchronization and atmospheric delay errors. So differential GPS develops on these techniques and gives you an accuracy of 15 centimeter, which is good enough for orientation estimation on big objects like ships and planes, where the GPS receivers can be very far apart. However, on a small drone, clearly the target is much higher, and what can we do to reach there? So this particular kind of differential, we can call this as spatial differential, because we are subtracting carrier phases across different receivers which are separated in space. Now, the obvious counterpart is time. Can we leverage time differentials as well? And the answer is yes, but there is a trade-off. So here I've expressed the same equation you saw in the previous slide, but it is time-stamped with T1. When the receiver pair moves, you can express a similar equation time-stamped with T2. Now, over T1 and T2, the integer ambiguity can be tracked because we can track the Doppler shifts, more details in the paper. But the high-level message is that the right-hand side is completely free of integer ambiguity. However, you are measuring only the change in relative vectors that can only give you the change in orientation. So clearly, there is a trade-off here, something to think about. So at this point, I would like to take a step back and summarize what we have learned so far. We made two observations on orientation. On the one side, we have spatial differentials, which give you a measure of relative vectors and hence absolute orientation of the drone, but it is heavily polluted by integer ambiguity. And on the other hand, you have these temporal differentials, which can measure the change in relative vectors and hence change in orientation, but it's not polluted by integer ambiguity. You can think of this as analogous to compass and gyroscope, which gives you absolute and relative orientations. However, they are very highly noisy. And in the rest of the paper, I'm going to explain some of the filtering techniques that we have done in order to make best use of the information from these two different perspectives. So we take a Bayesian filtering approach in which we model the state of the drone as orientation. And as the drone flies in space, its orientation will evolve continuously. And different states are linked by a transition function. Each state gives a measurement function which captures absolute information of the state. So the two perspectives we learned so far can be mapped to the transition and measurement functions respectively. So let me elaborate. So we saw that the temporal differentials was capturing the change in relative vectors. From that, we can derive the change in orientation, which is our transition model linking the successive states. And the spatial differentials give us the relative vectors, which can be used for tracking the absolute orientation, and that becomes our measurement model. However, I began by explaining that estimating integer ambiguity is a very difficult problem, and we still haven't addressed yet. So how can we resolve integer ambiguity? So there is no one solution. There is no silver bullet. The actual solution depends upon regimes of flight aggressiveness. Under low dynamic flights, because the error distribution are Gaussian-like, we can use a Kalman filter-based approach for combining the two perspectives. However, under highly aggressive regimes, because of a phenomenon called cycle slips, you will have integer errors in multiples of wavelength. Therefore, we develop a particle filter framework in order to handle such cases. So let me explain them one by one. So under low dynamic flight, assume that the drone started in a known static state with precise known orientation. Now, at the next time instant, T2, we can use the transition model and the previously known orientation to obtain the new orientation. Let's call that Q2 hat. And on the other side, we have the measurement model. So let's use Q2 hat for resolving the integer ambiguity in the measurement model. And once we do that, we can re-estimate orientation from the measurement model. Let's call it Q2 tilde. So under low dynamic flights, the error distributions in these two estimations are going to be Gaussian-like. Therefore, we can combine them using Kalman filter to achieve the most likely orientation estimate. However, under highly aggressive regimes, everything breaks. Because of a phenomenon called cycle slips, your transition model will fail. Therefore, the resolution of integer ambiguity will be bad, meaning the entire chain of Kalman filter is derailed. And in order to address this issue, it turns out the key question we need to answer is how we can identify incorrect resolution of integer ambiguity. So in order to do that, let's start revisiting our measurement model. And let's rewrite the equation a little bit. So the left-hand side is an integer. The right-hand side should be an integer ideally, but because of erroneous estimates, it won't be a perfect integer. It will be very close to integer. So if we take cosine on both sides of this equation, the right-hand side should be very close to 1. And we developed this metric called cos metric, which is the sum of these cosine terms over all possible satellites and GPS receiver pairs. When the cos metric is very close to 1, we have sufficient confidence that the integer ambiguity is correct. However, when the cos metric deviates substantially from 1, that gives us a hint that, hey, something is wrong. We need to fix this. So now that we have a hint about when things are wrong, how can we correct it? So let me walk you through the process. So assume that we started in a low dynamic regime, and as long as the cos metric indicates high confidence, we can keep doing Kalman filter. However, when the transition to aggressive regime happens, and there is indication of poor confidence from the cos metric, we can trigger particle filters. These particle filters are essentially tracking multiple integer ambiguity spaces in parallel. And we can propagate them using the transition model. So over time, the particles tracking the wrong integer ambiguity spaces will diverge because of poor mismatch between their transition and measurement functions. However, the correct particle will converge, and at that point, we can continue with Kalman. And again, if there is low confidence in the cos metric, we can revert back to particle filter. So all of this worked out very well, except for one problem. There was slow convergence in the particle filter. So in a simple particle filter, we propagate all of these states to the next time point using the transition model. And we weigh them using the measurement model and assign probabilities, which is later used for filtering, and so on. So such method required a huge number of particles. However, by exploiting the nature of integer ambiguity, we made a simple modification. So we combine the transition and the measured observation using a Kalman filter-like approach, and we propagate that particle instead. So because of the nature of integer ambiguity, this results in an accelerated convergence for correct particles, and at the same time, it results in an accelerated divergence for wrong particles, resulting in an overall convergence with much fewer particles. So enough of theory. With this, let's get into practice, and let's see how well all of this works in reality. So this is our evaluation platform, the drone from a commercial manufacturer, and we put multiple GPS receivers which are connected to a Raspberry Pi. And like the drone has inertial sensors, and we have a GoPro under the drone for giving us high precision vision ground truth. So vision itself is not going to be a solution because it is computationally intensive, and it requires several hours of offline processing for getting a converged solution. However, for evaluation purposes, it's a very high precision ground truth. So with this platform, we compare the performance of GPS orientation with inertial sensing. And here is a flight trace. On the y-axis, you see the tilt orientation angle over time. Clearly, this is an aggressive flight because there are sharp changes in these orientation angles. And if you look at the performance of safety net, we are closely tracking the vision ground truth, even under sharp angles, suggesting substantial promise. And here is the breakup of error over on the y-axis over different regimes of aggressiveness of the 3 orientation angles, yaw, pitch, and roll. So even under highly aggressive regimes of 100 degrees per second of angular velocity, the 95th percentile error is less than 8 degree, and this is a very good feature to have. And here is the overall error distribution of both the tilt orientation and the heading orientation angles. And the takeaway is that the median error is about 2 degrees, and at the 95th percentile, the error is less than 8 degree, and we are comparable to inertial sensors. So let me summarize. So despite excitement, poor reliability of inertial sensors is becoming showstopper for many drone applications. We developed an orthogonal solution for orientation sensing using GPS receivers, and we developed a systematic solution based on particle filter for handling dynamic errors from carrier faces, and real extensive flight tests demonstrate substantial promise. So with this, I conclude my talk, and I'm happy to take more questions.